We are going to start section 2.2 today, which deals with taking a normal curve and using it to model a distribution. So today we're going to talk about what's called the 68, 95, 99.7 rule. So you'll see that momentarily. And then we're going to focus on the standard normal distribution for the next couple of days, which really allows us to compare different distributions, look at different percentiles, and they're very useful for us in statistics. And in order for something to follow those rules, that distribution has to be approximately normal. So later in the week, we'll talk about how do we assess whether or not a distribution is normal so that we can use the calculations that we're going to learn about in the next few days. So, like I said, we're going to work with these normal distributions. And so normal curves are going to be following this bell-shaped curve that you may have heard about. So all normal curves are going to be symmetric. They have a single peak and they are bell-shaped. And so all normal distributions differ, and they're described specifically by its mean and standard deviation. So the notation that we usually see to denote that a distribution is normal is a capital N for normal, and then in parentheses, we see two numbers separated by a comma. The first one is mu, and again, this is our population mean. Remember that X bar that we saw in chapter 1 was our sample mean. So this mu is describing the entire group. X bar just describes the sample or the subgroup. Sigma here is our population standard deviation. So in chapter 1, we focused on S sub X. That was our sample standard deviation. Sigma is the standard deviation of the whole group of the population. And so looking at these two curves here, you can see that this first one is shorter and more spread out. It is shorter because the area under the density curve always has to be equal to 1. So in order to kind of compensate for the horizontal expansion, the peak has to come down. The wider your spread is, the larger your standard deviation is going to be. This curve over here on the right is fairly narrow, it's fairly tall. So here, this is going to be a smaller sigma. Because remember, standard deviation tells us how far on average values tend to fall from the mean. So if it's a small standard deviation, values are going to be pretty close to the mean. Large standard deviation, values are going to be pretty far from the mean. So for normal distributions, like I said, we're going to describe by a normal density curve. Any normal distribution is going to be described by its mean and standard deviation. The mean of a normal distribution is going to be the center because it's a symmetric normal curve. And then the standard deviation is the distance from the center of the curve to its inflection point, or the point where it changes curvature. That's not something that you're going to have to locate that point or really draw it accurately. But for those of you that are maybe in calculus, you've heard about inflection points. That's really what's happening here, because eventually we're going to find the area under these curves using ideas from calculus, but we're going to focus on using technology and tables to help us find the area. And as I had mentioned on the last slide, we have that abbreviation here, and you should recognize this notation. So it's not something that you have to use, but it is something that if you're provided with that, if you just have a capital N with two numbers, you need to know which is the mean and which is the standard deviation. So why do we need these normal distributions? A lot of times real data follows this bell-shaped trend, and then we can use it to answer questions about the population, which is really what we do in our inference procedures in the second half of this course. And then also when we talk about chance outcomes, a lot of chance outcomes are going to be well modeled by normal distributions. So here we have what we call the 68, 95, 99.7 rule. This is also known as the empirical rule. And you guys saw this in the video that you watched on the Boston Beanstalks. They talked about the 68, 95, and 99.7. If you have a distribution that's approximately normal, then we can say that about 68% of observations are within one standard deviation of the mean. 95 within 2, and 99.7 within 3. So you can see those values come up on the sketch below. You've got 68% in that light blue, 95%, and then 99.7 as you extend out. And so one thing that I do want to mention is that the curve is symmetric. So you can break this down. Like if I break the curve in half, I have 50% to the right of the mean. I have 50% to the left of the mean. I can also break this 68 in half. I can break it into 34 and 34. And I can do similar things with the 95. I can break that down into 47 and a half on one side, same on the other. And then even with this like 99.7, I can say, okay, there's 0.3% of the distribution left and it's split in half. So you really have 0.15% in this top extreme, more than 3 standard deviations above the mean, or 0.15% in this bottom extreme, more than 3 standard deviations below the mean. So just know that you can use symmetry to break up any of the sections of the curve. So here we're going to look at an example, and you see that we do have that normal notation here, so mu and sigma. We're going to sketch that density curve, and then we're going to use it to answer some questions. So what percent are less than a certain value or between a certain value? So when we sketch the distribution, we draw ourselves a symmetric bell-shaped curve. We put the mean in the middle here, so 6.84, and then we just count up by multiples of the standard deviation. So 6.84 plus 1.55 takes us to the 8.39. Add another 1.55 and a third 1.55. And then going the other way, if we take 6.84 and we subtract 1.55, that takes us to 5.29, subtract again, and then a third time. So that would take care of part A. Part B says what percent of vocab scores are less than 3.74. So that's this value right here, and we want less than. So we want everything to the left of that value. So in order to do that, there are a couple of ways that we can respond, but the easiest way, I think, is what's shown here, is that this is 2 standard deviations below the mean. So we know that we have 2 standard deviations corresponding to 95%, as you can kind of see here in the shaded red. So there's 5% of the distribution left over, but we only want the bottom half. So if we take that leftover 5% and divide it by the 2 tails, we have 2.5% or less than 3.74. That would be part B if we label. And then part C over here is scores between 5.29 and 9.94. So here you've got 5.29, here you've got 9.94. Again, there are multiple ways to go about it, but the method that you're seeing shown here is this 5.29 is 1 standard deviation below. So we can go 1 standard deviation on either side, and that gives us 68% of scores. But then we still need this additional area here that's highlighted in green. So in order to figure out what that's going to be, within 2 standard deviations, so 3.74 to 9.94, that's 95%. But we've already accounted for this 68. So we're going to take that 95%, subtract the 68% off, but then we only want the top half. So that's this 13.5 here. So that 13.5 plus the 68 gives us what's between those 2 values. So I'm going to walk you guys through a few problems in this empirical rule worksheet before you're done for the day. And then for homework, you'll finish that worksheet and then work on the book work. So let me go ahead and switch to the worksheet here. Okay, so on the empirical rule worksheet, you have a sketch of the normal curve with the 68, 95, 99.7 kind of outlined on there for you. And then we have some questions to answer. So what some students like to do, instead of drawing the whole curve just to save space, is that they'll just draw a number line. For homework, that's okay, but for tests and quizzes, you really should put that whole curve in there. So here we have IQ scores have a mean of 100, so we're going to go ahead and put that in there, and then a standard deviation of 15. This question is asking us for between 70 and 130. So once we get to those values, we don't have to keep marking off standard deviations. So for example, 100 plus that standard deviation of 15 is going to put me at 115. Another is going to put me at 130. I don't have to keep going to 145 here. I can stop and see that 130 is 2 standard deviations above the mean. On the lower end, I'm going to subtract 15. So if I take 15 away, that's going to put me at 85. And then if I take another 15 away, that's going to put me at 70. That's my lower bound for what I'm looking for. So I don't have to go another 15 away and put down a 55 here. So I want this area that's within 2 standard deviations. That corresponds to 95% of the distribution. So this next one here, we're looking at heights of men, and this one asks us a couple of questions about it. So I'm going to go ahead off to the side and draw my curve. Put my mean in the middle, which is 176, and then I'm counting by multiples of 7. So that'll put me at 183, 190, and 197 on the top end. And then on the bottom end, I'm subtracting multiples of 7. So that'll put me at 169, 162, and 155. So here I'm looking at for part A, 169 to 183. That's here to here. So that's just 1 standard deviation in either direction. So it's going to be 68%. And then part B is the 155 to 197. That's 3 in either direction. So that's 99.7% of the distribution. So here's where it may get a little trickier. In question 3, you're working backwards. So they're telling us we've got our mean and standard deviation for heights of women. And we want to figure out 84% of women are taller than a certain height. So we have some certain height here that we're trying to find. The mean is 64.5. And we're looking for 84% to be to the right of this cutoff height. And we have to figure out what that cutoff height is. So in order to figure that out, we want to try and see how we can come up with 84%. So we can kind of think about, okay, we have, if I sketch over here, the mean, and then you've got 1 standard deviation below and 1 above. This is going to be 68%. So then we can figure out what's left over up here, or we can think about it this way. There's 50% to the right of the mean. With this 68% here, we've already accounted for this side on the right. So that is half of the 68, or 34%. So there's another 34% over here. So 50% to the right of the mean plus that 34% is going to take me up to that 84%. So it's going to be 1 standard deviation below the mean. So then I just have to figure out that value. 1 standard deviation is 2.5. So if I take 2.5 away from 64.5, that'll put me at 62 inches. So for your assignment, you can go ahead and try to finish the back of the worksheet, and then we'll go over that in our next meeting and move forward with section 2.2.